Good to be here. So my name is Jason Priestley, as Ryan said. And let me just get set up here for a second. So the topic of my talk is structure editing combinators, and this library that I've written that provides structure editing combinators for Haskell. And of course, structure editing combinators is not really something you've heard of. It's kind of my attempt to describe this, but it hasn't really been done before, to my knowledge. So the combinators part, probably a lot of you are familiar with that. If you've used the library Parsec for parsing, that provides combinators for parsing. And it's kind of a general technique to build up something complicated from simple elements and then combination rules. So in this case, what we're building up is a structure editor, which is also called tree editor, or I think there are a couple other names for it. But it's not been done too much. But that's the origin of my name for it, treersec. It's tree plus parsec, because you're using parsec-style combinators to build a tree editor. So the first question is, what is a structure editor? And I'm going to start by saying what is a normal workflow for editing a language, for editing a programming language. Or something else like a configuration file, the kinds of things that you would use a parser for. So text-based languages, you have a grammar for the language, you have a plain text representation, and you just store those in text files. You edit them with your favorite text editor, Emacs obviously. You do version control at that level. So your Git or Mercurial or Darks is going to be looking at the text that you're writing. Then you have parsers. Definitely one of the most interesting, well-developed areas in computer science. The parser transforms your text into a tree structure. So you start with 1 + 1, and you get a tree with plus at the top and two children of the two operands. So that's called the abstract syntax tree, or AST. And then the AST typically is used for a lot of the other things you do with a language, including type checking, optimization, code generation, which is building the actual machine code that allows you to run that language. If it's an interpreted language, then you just run the AST directly, basically. And there are some operations you want to do on a language that are kind of awkward under this scheme. And these are sort of the IDE type features. So autocomplete, syntax highlighting, debugging mode, where you're in your editor and you see where you are in the file. Live preview, where as you're typing, it's updating something. And the reason these are awkward is that you want these to be working on kind of a partially finished version of the file. You have to be taking the text you've typed, translating it into an AST to figure out what could you autocomplete here, what kind of syntax is this, and then translating that back into text coordinates. And parsers, typically, parsers are not written so that they'll even work when you don't have a correct program. So if you want syntax highlighting even when you have like an extra parenthesis somewhere in your file, then it's extra work. And actually, most syntax highlighters, I've investigated how they're implemented, and the syntax highlighter in your favorite editor is probably just using like some pretty dumb regular expressions to kind of get it 95% right. So the structure editor in contrast to that paradigm, to the text-based paradigm, it uses the AST for everything. So you never have a plain text representation of your program. And this means that you need a way to edit your AST, because you can't edit the text and parse the text into the AST. So structure editor is just any UI that directly edits the AST and doesn't create a textual representation as an intermediate. Version control has to be redone for a structure-based paradigm as well. That's not covered in this talk at all, and I don't really know that much has been done on that front. And the one advantage of the structure editor is that those awkward features, they become much more natural. A disadvantage is that you're throwing away a lot of pre-existing software. So I wanted to talk a little bit about the reason that I'm kind of interested in structure editing before getting into the details of what I've written as a structure editor. So the larger vision is that I think that the way that we write interactive programs now is a little bit broken, where you have these monoliths, these kind of silos of functionality called applications. So you have Photoshop or Microsoft Word. They're huge pieces of code, and they're very isolated. I can't do anything to a Word document with Photoshop and vice versa. They can't share any code. And actually, they should be able to share a lot of code. A lot of what they're doing is manipulating lists, doing history manipulation with stuff like undo or words track changes. So I think that a better UI paradigm would be something like Emacs, where in Emacs you can really add very granular plugins to modify a particular interaction. You can swap out the piece that allows you to search through files, for instance, or you can change the syntax highlighter and let everything else be the same. And I think a barrier to extending that kind of paradigm into a full computing environment is the fact that all of our programming tools are text-based. So there's kind of this big barrier between you can do all kinds of cool stuff with text, and then once you're dealing with something like an image or a widget, a slider, it's not nearly as natural. Think of even just taking a programming language and adding a slider to some data type. It would kind of be a huge project as it is. There's no natural way to put that into the parser, into the editor, etc. So that's the overall vision, which I see the structure editor as kind of a building block for that, a first step. So this is a high-level overview of what goes into the structure editor I've written. One thing about structure editors, text editors, they're kind of all going to be the same, because just the nature of what they do, you have to show the text in a certain way, because that's the expected way that text is going to look. You have to lay it out, in rows and columns, so that your ASCII art looks correct in this new text editor. You have to be able to select a range of text and so on. So there's a lot of constraint on what a text editor looks like. And there's really none of that on what a structure editor looks like. One example of a structure editor actually is the program Scratch, which is used to teach programming for children. And it kind of has a UI of like Lego blocks, and you drag them together. So that's editing the tree, I believe. I don't think there's a textual representation there. And it's obviously just very, very different from a normal text editor. So there are a lot of choices that go into building a structure editor. It's kind of an open field in a way that a text editor is not. And the one I've written, it's pretty close to a text editor. It's not as radical as like Lego blocks or a visualization of the tree or anything like that. So I'm going to go through the different parts of it, which are, there's the interactive parser, which is how you enter stuff into TrierSec. There's the pretty printer, which is how you see what the tree looks like right now. Selection is something that is just obvious for text. Text is an array, so selection is a subarray. In the tree editing context, you have to ask what is a selection. And then finally specifying the grammar, which is just how you actually get this working in Haskell. The interactive parser, if any of you know about a little bit about parsers and parsing theory, the interactive parser is based on an LL grammar. So an LL grammar is, roughly speaking, is one where when you see the next piece of code, you already know what kind of tree construct it's part of. So the LL grammar gives rise to a very simple parsing algorithm, the recursive descent parsing algorithm, where you just look at the next token and try to add it to the current tree, and then go on to the next. The interactive version, you simply use the same algorithm. You find the same tokens that could come next, but instead of trying them out, instead of trying to parse that out of the stream of text, you just ask the user, what's the next token? And what this is as a UI is a sort of autocomplete input box. So you can type in tokens like a semicolon or a brace or a string or a variable. And the one I've written is very primitive, but I think as I develop this into more of a real programming language, the autocomplete input box is going to be the basis for a lot of advanced functionality. For example, you could offer names that hadn't been imported yet, and then when you choose them, it could import that into your context automatically. So the LL parsing algorithm paired with the auto-completing input box, that already lets you input from A to Z the whole tree, because that's how it works when you're parsing a text file. If you already know the whole code and the parser is just going through it. There's a bit of a wrinkle when you're using it as the basis for a structure editor, which is that you might be in the middle of a partially completed tree, and then you need, you still need to add something. The example I have is a grammar for a list of A's. So it just has one production. The A production is either an A followed by a list of A's, or it's nothing. So suppose that you have some text, which is a list of A's, a list of 4 A's, and you're trying to insert something in the middle. So in this case, the tree is already complete. There's a left child, there's a right child, everything's filled in. So the question is, how do you offer that A that you want to insert? And the solution I came up with is to look at the grammar and look for these kinds of recursive rules, where A, if you expand it out, is going to be some number of tokens, A, B, C, in this case just A, and then a recursive call to A. So whenever we see that pattern, we can allow the user to insert the tokens that come before the recursive A, and then we kind of perform surgery on the tree. We take the branch that goes onto the recursive call, and we pluck it out, and we put in whatever token they used, and paste back in our dangling node in the recursive position. Yes? So the question was, does that mean that at any given time the tree is a valid parse tree? It's a good question. The answer is it's almost a valid parse tree. In some cases, let's say you had just XYZ as the production. So when you fill in X, you don't want to fill in Y and Z immediately, so those get placeholders. There's a special node type which is placeholder. But otherwise, it always matches the grammar. It's just that under some circumstances, let me think of an example. Well, you generate a new subtree, yeah, but it's always following the grammar. So yeah, we use the structure of the grammar to give you these extra options. So that's kind of the main tricky points of the input algorithm. Obviously, the code has some extra finesse, but really it's a very simple algorithm that I've written. I've really tried to follow the spirit of recursive descent parsing, which is, it's not the best parsing algorithm, it's not the most efficient, but it's just so simple and so flexible that it makes a great basis for experimentation. And I'm hoping that the algorithms I've found for ChurSec will kind of fill the same role for structure editing. So now that we have our input box, we want to see our current tree in some representation, and then we want the input box to be in there for us to edit our tree. So the pretty printing algorithm I use it's pretty basic. I kind of just came up with it in a day and haven't really optimized it yet. I just have a list of the optimal layout at a given width, and then a few combinators where when you place two things beside each other, it goes through the list of widths and pairs together the ones which have similar heights, so that generally you minimize the total height. I think that's a good heuristic for code that doesn't look too bad. Pretty printing, I think, is a really neat part of the structure editor. I think before I started working on this, I wasn't really cognizant of how annoying ASCII text layout actually is. But since I started writing this structure editor, I'm just always noticing, like, oh, I have to like reorder all these braces and like figure out a way to get this to display on lines well. And you know, editors help to a good degree, but I think that pretty printing is going to bring things to a really higher level where we'll be able to try different algorithms for laying out code. We'll be able to use two-dimensional layout. So if you imagine something like an object between two big curly braces, and then an equal sign, and then another object between two big curly braces, these are the kinds of things you can see in a mathematical formula, but we programmers have mostly just stuck to lay the first big thing out on lines and then the second big thing, like maybe gets indented correctly or not. And then the other nice thing is it's just the computer taking care of things for you. No more arguments about how to lay out code. No more thinking about it as you're typing your code. And if you have different screen resolutions, then the computer should be able to handle those. Yes. The question was, did I ever read up on epigram regarding 2D layout? I have not. I haven't heard of that. Cool, I'll definitely look that up. Thanks for bringing that up. All right, so yeah, not a lot to say about pretty printing, partly just because I haven't really come up with anything that original or neat. It's just a very basic one right now. Selection. So as I said, with a structure editor, there are a lot of choices. And there are choices for selection. You could actually try to simulate the text range selection. So if you click in the middle of a string, you could select from the middle of that string. I think some structure editors will select using the tree structure. So you could be selecting the parent node or one of the child nodes or both of the child nodes, and these are all distinct selections. I chose to go with a selection is a node in the tree, and I'm not distinguishing between two nodes if they have the same leaves. So if you see a certain set of tokens as highlighted, then that's the same selection. There's no extra UI to be selecting their invisible parent. And if a selection is a node in the tree, then it gives us this problem with recursive grammars again, where here I have the list of A's again, and you're trying to select the middle two A's. That's a sensible operation, just select the middle two A's and get rid of them, for instance. But if you're selecting a node in the tree, then the last four A's would all be the tail node. And the solution to that is just basically the same idea. Have a special case for tail recursive grammars, and in that case allow a selection of node 1 minus node 2, which is the same production. So that's all for how I implemented the editor, and here's how you build these grammars. So if we start with a grammar in like normal context-free grammar notation, I'm not sure if all of you are familiar with this, but it basically says an A, a capital A, can be represented as a lowercase a and then a b. A b is always a comma and then an a, or a b is a epsilon means nothing. So this means a becomes ab, b becomes either nothing, in which case we have an a, or b is comma a, and then a could be another a. So this is a grammar for a, comma a, until b is nothing, and then you have nothing. So it's a list of a's separated by commas. To get this into Haskell, we just kind of mechanically transform it. We combine the alternatives into a list. So b had two alternatives, and it becomes comma a or epsilon. We consolidate the productions by substituting them in. So a was expanding to A and then B. So we just inline the definition of B. And then, of course, if you followed this strategy with A as well, then you just get this infinite loop of inlining. So these recursions where A expands to A, we use a sort of lambda to capture that as an explicit sharing relationship. And then we translate to Haskell. I don't know if it's very clear that this corresponds to the structure, but it is a very mechanical translation of the previous slide. You have your lambda thing, which is gfix, and then literally a lambda. Alts, so that's alternatives. And this is just a single alternative. So the only alternative is term A, means just a string A. And then the second element of that alternative is another alternatives. And this one has two alternatives, the empty one or the comma followed by going back to that lambda. And then we have these PP besides. These are functions for the pretty printer. So you can customize how each term is laid out. In our case, we're just using the same basic combinator each time. This syntax is going to change almost certainly, because one weakness of this, besides just not looking that great, you can't extract a value from these editors right now. So what I'd like to do is have a type associated with each grammar, and then you apply a function. So you have a grammar A and a grammar B, and you apply a function A to B to C to build up your result. And that's how you do it in Parsec with the functor instance. So to do that, I'll have to introduce an auxiliary type with some kind of type tags, like GADTs or something, so that I can keep track of the types of individual pieces. And at that point, we'll have some kind of denotation probably. All right, so that's it for the exposition. So I have a demo, and this is going to cover a slightly more interesting example, I hope, than the list of A's, which is JSON. So this is the code for what you're about to see. JSON is of type grammar A. And you can see it's using those same types, gfix, alts, but there's a bit more structure here since it's a more complicated grammar. The nice thing about the combinatorial approach is that everything's just a normal Haskell object versus, say, parsing in a special case syntax. So we can use where to go into detail about, here's the code for a JSON object, which has an auxiliary KV pair, the code for a JSON array. Simple is just a string and number.
What languages have you written parsers
for? Using this syntax, I mean, I've just developed this. Sorry, the question was, what languages have I written parsers for using this syntax? And basically, yeah, this was not working like a month ago, so I've been, it was kind of a race to get even JSON working for this talk, to be honest. So this is the result, and it's an empty JSON array. the hash sign is indicating a placeholder. So it's a part of the grammar where something is required, but there's nothing to fill that node because the user hasn't entered anything. So I'm going to type I, which just means input before the selection. And you can see the autocomplete. It's context sensitive, so it knows exactly which tokens are available. Right now, only the comma is available. We can create a list with 1, 2, 3. You can see that you can select ranges. One thing you'll notice is you can't select like comma to comma because that wouldn't really make sense. If you removed that, for instance, what would you be left with? 1, 3. It's not a valid list. So just because the grammar has a certain structure where the recursive nodes are only in certain places, that selection is not allowed. So I got rid of those, just hitting a key to activate the delete command.
So why don't you insert a number of those? First number. It shouldn't be a correct parse. You have to either type the number of the comma, right? And until you type those,
So the question was, when you're adding something in the list, in the middle of the list, if you add a number, then it would be invalid without a comma as well, because you need a comma after your added number. So how to deal with that? And the answer is the comma is added as a placeholder. Anytime there's a required element that the user has not input, it becomes a placeholder, so that the tree structure is still correct. What's that? Yes, the grammar is deterministic. So I'll just type in a few more things just to show off the pretty printing, such as it is. It's a very simple algorithm, but you will see it adapting to how wide. See it ran out of space because I've only given it like 500 pixels. So I took that list and reoriented it to be laid out vertically. And I didn't get to this before the demo, but I'd like to have more of a mathematical layout where you have 1 and then hello world would be in probably large brackets and centered within the list so that you can really see this is a list of 3 elements and one of them is this big list with hello and world. That's about all that the demo is capable of for now. But as you can see, you can. There's also a pretty serious performance issue with the JavaScript compiled stuff. I think it's because I'm running the pretty printer on each frame. So yeah, that's it. Are there any questions or comments? Yes.
Quick, you said that you need special version control if you want to deal with this stuff, but couldn't you just have a pretty printer or a not so pretty printer that just dumps the whole structure out to a predictable format, version control that, and then make sure it's an invertible transform, and that way you would be able to punt on the version control for now?
That's definitely an option. I think, I mean, it would definitely get you some kind of version control without a whole lot of effort. The downsides would be that if you messed up merging two trees, I mean, first of all, the tree representation has to be readable so that you can go through the merge, and then if you mess up merging them, you need a parser that can tell you where you went wrong. So you end up having to include some of the traditional parsing facilities. Still might be an easier path than writing a customized tree-based version control system. Yes, did you?
Just briefly, on that, there's a lot of structured work done that's in the literature. The downside, and there's two of them. The downside is it's all in context of HTML. Or sorry, XML. Because that's what the core version we're interested in, XML version. But structure-safe merging has a lot of good literature. If you're willing to go the intermediary XML representation, just as a hack, then you can even leverage your existing toolbox.
That's interesting. I hadn't thought of looking in XML literature. I think actually if I see XML in a paper, I'll probably just skip it. Yes? Yeah, so the question is, with restricting selection to syntactically valid selections, aren't you cutting out things that do make sense? For example, if you actually deleted comma to comma, you'd end up with 13, which maybe you're going for 13. These are the kinds of things you can do in a text editor. Delete some kind of random syntax and end up somewhere that you want to be. I think it's a trade-off. I think that sometimes you do want, I notice myself that sometimes I edit pieces that would not make sense syntactically just because I notice that the piece over here is exactly what I want to the left of the piece over here. I'm inclined with TrierSec to just explore keeping things to syntactically valid selections, because I think it allows us to make more guarantees about the state of the system and give you better tools on top of the basic selection. Because as it is with just the selection I have, it certainly is more limiting without really any benefit than the text-based selection. Yes? I'm not sure I understand. Right. Yeah, so the suggestion is when you do something that would invalidate the tree, we could show what is invalid about that action and what they could do that would be valid. And yeah, I agree that would be, like the current system, if you try to type in a token that is not available, it'll just ignore your key presses, which is not the most user-friendly. So I do think that there should be some correction to the user immediately. It's not as possible to, or not as good to try to allow you to enter this invalid data and then like give you a flag that you did something wrong, because then you have to deal with this persistent invalid data, and all the algorithms have to deal with the fact that the tree might have incorrect tokens inside of it. Yeah, it could work. Yes?
I was actually wondering, or actually going to post a little time, I was wondering if this would actually allow the user to create correctness on a higher level. I was thinking a classic example that would work very nicely in your system would be the dangling else problem in languages like C and C++, where you have an if clause without an else inside another if clause, and you want the else to go to the upper one.
Mm-hmm.
And this, by editing the structure instead of the textual representation, going, I want to do this if statement, not the one that it just happens in the inner one. And I'm just wondering, have you thought of being able to do correctness at that level?
Right. So the question was, would this system allow you to correct problems like the dangling else in C, where you have an if clause without an else, and then it's nested within another if clause, and you want the else to go on the outer if clause. So the system I've written it's very tied to the grammar. So you'd need to make an unambiguous grammar and then get your tree to the state where it's following that unambiguous grammar. So you couldn't have a grammar with a dangling else, for instance. There are other approaches to tree editing where it's more, you're seeing more of the tree. It's more like stuff like you have commands for move up a node or move down a node or select children, and in those cases you can more do these kinds of operations of saying I don't want to change the text at all, but I just want to move this this part of the tree to this other part of the tree. Yes.
So, most languages are not thinking of LL grammar, K grammar, points coming out with different like interesting languages. Do you have limited like early parsers or something that would actually let you predict all possible completions coming out of
So the question was, since most
the recursive intent parsing actually has to be backed up on the possible parsers. So it's the early parser, keeping all the same.
So the question was, since a lot of interesting grammars are not LL1 but are LLK or require infinite look ahead, or LR or just general context-free grammars, have I thought about building this tool to allow on top of something like an early parser, which can handle a wider range of grammars? Part of what makes this tool kind of elegant is that the autocomplete is just a drop-in replacement for the token look-ahead in the LL parsing algorithm. So I'm inclined to just say, figure out a way to make your grammar LL1. I think that I mean, you definitely could use a different grammar to generate a list of tokens. The problem with something like an LRK grammar, it gives you a list of tokens that can follow, but you don't yet know what tree structure those tokens are going to have. You don't know until you finish the production. So you'd have to have a much looser representation of the parse tree with stuff like unparsed tokens in there. Sure. Any others? I think I should mention also, I forgot to work it into the talk, but there are other very interesting projects going on in this area in Haskell. I know that there's one called Lambdo, which is trying to make I believe, a structured editor with a lot of type-related machinery, so that you can refine your types as you're editing. There's one called Unison, which I think is a kind of structured editor, and this is Paul Chisano, and he's going even further. He wants to prevent you from entering an ill-typed term. So it's not just syntax errors that would be gone, but type errors, which is even more ambitious. All right, so thanks everyone for listening.